Hello everyone, today we would like to talk about accelerated coordinate system. Before that, let us introduce ourselves.
My name is Nur Aniswana binti Mat Zahid and my metric number is 2026127453.
My name is Cik Nur Anisa Yuni binti Cik Mastar. My matrix number is 2026117019.
My name is Nur Alia Maisara binti Muhammad Nizam. My matrix numbers 2026132445.
My name is Nur Hashimah binti Muhammad Aslam. My metric number is 2026129223.
Introduction. What is a non-initial reference frame? A reference frame that undergoes acceleration relative to an initial speed frame. In classical mechanics, Newton's law holds only in inertial frames. When we observe motion from an accelerating not because any real force acts on the particle, they have two types, which is inertial frame and non-inertial frame. For inertial frame, they have fixed or constant velocity observer. Newton's second law applies, no fictitious force, and for example is ground observer. For inertial frame, accelerating observer, extra fictitious force term appears. For equation, F equal to F real minus m a naught, and for example, potential in accelerating car.
Okay, next I will explain the concept, equation and law derivation. Based on the figure 1, let O be the fixed initial origin and O prime be the moving accelerating origin. A particle at position J is observed from both frames. The characteristic is the frame is accelerating. Newton's second law cannot be applied directly and an initial force must be introduced. Next, I will explain the equation. R represents particle position in initial frame, R naught represents position of moving origin, and R prime represents particle position in moving frame. Based on the R, R naught and R prime, we have the equation which is R is equal to R naught plus R prime, and we must differentiate it to get the velocity. dr over dt is equal to dr naught over dt plus dr prime over dt, and we got velocity v equal to v naught plus v prime, and again we must differentiate to get acceleration, and we get a is equal to a naught plus a prime is total acceleration at moving axis, and we must know that v naught represent velocity and a naught represent axis. Okay, next, based on the figure, we have two situations. The first one, if the moving system is not accelerate, which means a naught is equal to 0. So we just use formula a is equal to a naught plus a prime, and we substitute a naught equal to 0, and we get a is equal to a prime. The next situation is if the moving system is accelerate, we use formula f is equal to ma, and we substitute a is into the formula, and we got f equal to ma naught plus ma prime, and we know that f prime is equal to ma prime. So the last one we get negative ma naught is translation force.
Now, let's talk about the concept of accelerated coordinate systems applies in our daily life. An accelerated coordinate systems is a non-inertial frame of reference where we introduce fictitious forces to explain motion. Although these forces are not real physical forces, they help us understand what we experience in accelerating or rotating systems. Example 1. Elevator. The first example is an elevator. When the elevator accelerates upward, we feel heavier, and when it accelerates downward, we feel lighter. This happens because the acceleration changes the normal force acting on our body, causing our apparent weight to change even though our actual mass remains the same. Example 2. Car braking. The second example is a car braking suddenly. When the car slows down, passengers tend to move forward due to inertia. From inside the car, it feels as if a force is pushing us forward, but it is actually a fictitious force caused by the car's deceleration. Example 3 is amusement park ride. The third example is a spinning amusement park ride. As the ride rotates, riders feel like they are being pushed outward. In reality, the ride provides a centripetal force that keeps us moving in a circle, while the outward sensation is explained by the centrifugal fictitious force. Fourth example is rotating Earth. The final example is the Earth rotation. Earth is a rotating reference frame. Moving objects experience the Coriolis effect, which causes them to appear to deflect. This effect plays an important role in weather patterns, ocean currents, and even aircraft navigation. To summarize, accelerated coordinate systems help explain many situations we experience every day, from elevators and cars to amusement park rides and the Earth's rotation. The concept of fictitious forces allows us to understand motion from different frames of reference.
So next we move to the question part. The problem statement here, a block of mass m is equals to 2 kg sits on a frictionless surface inside a railway car. The car accelerates forward to the right at a is equals to 3 meter per second cube. So here we need to find the fictitious force on the block as seen from inside the car, and second, the block's accelerations as seen from the ground, and third one is the block's accelerations as seen from inside the car. So next we need to use this equation, which is r is equals to capital R plus r prime, where r is equals to positions of the block in the fixed frame, while capital R is equals to displacement of the car origin from the ground origin, and r prime is equals to position of the block in the moving car. First step that we need to do is to differentiate the equation so that it will give us the velocity. As you guys can see here, we will get r dot is equals to capital R dot plus r prime dot. And next we need to differentiate it again to get the acceleration, where we get r double dot is equals to capital R double dot plus r prime double dot. So first question is the fictitious force on the block as seen from inside the car. So as you can see, we need to find the normal force, which is we need to use the equation W is equals to mg, which we will get the answer 19.62 Newton. And then we also know that net vertical force is equals to 0 because the block does not move up or down. So for the horizontal direction, we need to use the friction is equal to union plus Newton, which is 0 multiplied with 19.62, we will get 0. And next we move to the question, which is want to find the force, where F is equals to negative m plus a, where negative 2 kg multiplied with 3 meter per second cube, we will get negative n Newton. So moving to the second question, which is the block's accelerations as seen from the ground, fixed initial frame. So for this question, we need to use the Newton's second law, which is F is equals to ma. But we need to find the a, so we need to move the equation, which we will get a is equals to F over m, where F we got 0 and then m is equals to 2 kg, and we will get 0 meters per second cubed. So that is our accelerations. So we're going to move to the third question, which is the block's acceleration as seen from inside the car non-inertial frame. So we need to use this formula, which is a fixed is equals to a naught plus a related. So to prove the equation, which we will get a fixed is equals a fixed minus a naught, which the answer from the previous question, which is 0, so that's why f is 0, minus with 3 meter per second cube, and you will get negative 3 meter per second cube.
For conclusion, an accelerated coordinate system, not inertial frame, is one that accelerates relative to an inertial frame. Newton's laws in their standard form do not hold directly in such frames. A fictitious inertial force F equal to negative ma naught must be introduced to apply Newton's second law to motion observed from the non-inertial frame. The fictitious force has no physical source. It is an artifact, the observer's accelerative frame, not a real interaction between objects. The position relation r equal to r plus r prime and its derivatives unify the description of motion across both frames, providing a rigorous mathematical framework. Applications range from engineering design of vehicles and elevators to geophysical phenomena such as the Coriolis deflection of winds and ocean currents.